So homework 2 has been posted. It's a longer assignment based mostly on today's lecture, and the daily mini assignments will be updated shortly to be while you're in the StatMech lecture. The next week's mini assignments will be posted. So today we're going to begin our discussion of interacting quantum field theories. And we're going to start with the observable quantities that we can measure in a laboratory, namely the cross-sections. We're interested in a scattering process. A cross-section is a measure of the interaction strength, or how likely, in a sense, two particles are to collide in a particular way and interact, or decay rates, which are familiar. If we have an unstable particle, one property of that unstable particle we can measure is its half-life or decay rate. So it's going to take us several lectures in order to learn how to calculate these objects. So before we get started, with the calculations, I just want to outline where we're going over the next several lectures. So today, we're going to attempt to compute cross-sections and decay rates. And what we'll accomplish is we'll be able to relate these cross-sections and decay rates to amplitudes, or also known as S-matrix elements. So here, this is a Heisenberg picture expression. So we might be interested in the amplitude for some initial state to evolve into some final state. So S stands for the S matrix, and this we're taking a matrix element, the element for it to go transition element from some initial state to some final state, or we can also write this in the Schrodinger picture as we're looking at some state at future infinity. What's the amplitude to evolve from some initial state at past infinity to some future state at future infinity. So that's what we'll accomplish today. We'll relate these amplitudes to these cross-sections and decay rates. And then the next step, so that's progress, but we ultimately want to be able to compute these objects, and these objects are of interest for other reasons besides just computing these observable quantities. And so what we'll do next week is we will see that, well, it's difficult to compute these directly in the Heisenberg picture for an interacting field theory, basically because we don't know the time dependence of our operators. Can't figure that out. But by going to the interaction picture, we can relate these S-matrix elements that we're interested in to the time-ordered expectation value of a product of fields. Sorry, I skipped a step. So before I skipped a step. So today we'll relate this to these amplitudes. What we'll then do beginning of next week is look at the LSZ reduction formula, which will relate these amplitudes that we're interested in to vacuum expectation values of time-ordered products of fields. So here this is the time ordering symbol. And it just means put the operators that appear to its right in time order with the latest one to the left. We'll come back to that. And here, omega is the vacuum of the interacting theory. Okay. So this looks like progress. So the initial and final states we'll be interested in today will be momentum eigenstates. So we're imagining doing a scattering experiment where we send in a particle with some definite momentum and measure the momentum afterwards. And here, what we'll do next week is we'll relate that to a time order product of fields, the vacuum expectation value of that time order product. And while this is already looking like something you computed in tutorial yesterday, we basically were looking at just the vacuum expectation value of two fields. We didn't worry about time ordering yet, and we were in a free theory. But this is something that we have more hope of being able to compute than this. And we will be able to compute this by, as I mentioned before, going to the interaction picture. And we'll be able to relate this time-ordered product of the interacting fields in the Heisenberg picture to time-ordered product of fields in the interaction picture. And interaction picture fields are, it may not look like we made much progress here, but the point of going to the interaction picture is that interaction picture fields, even in a theory with non-trivial interactions, behave just like free fields. So these expectation values in the interaction picture are something we can compute much more easily than in the interaction picture, where we don't, in general, know the time, how the fields depend in time, field operators depend on time. And so here, this is the free vacuum that we studied yesterday. And these behave like free fields. And the last step will be we'll be able to relate this time-ordered product of lots of fields to the expectation value of the time-ordered product of two fields. Which is something which is very closely related to what you computed in tutorial yesterday. We just didn't have this time ordering symbol, and we were looking at outside the light cone. But you can repeat the calculation without too much change to get this time-ordered product of two fields, also known as the propagator. And we'll do this using Wick's theorem. So that's where we're going over the next 3 lectures. And then end of next week, we'll see that there is, in fact, a more efficient but entirely equivalent way to jump directly from the propagators all the way over to the S matrix elements. And this is Feynman diagrams. And I'll argue that this procedure, which you'll see is involves far fewer steps than the first time we'll do it, is entirely equivalent to what we'll do over the next few lectures. So that's where we're going for the next several lectures. So, goal is to be able to compute observables and it's going to be a rather lengthy process. I'll remind you where we are in this process periodically as we go through it. Any questions on that? Okay. So today we're going to focus on this first step, relating these amplitudes, S matrix elements, to cross sections and decay rates to measure in the lab. And well, first of all, I'd like to remind you a bit about what a classical cross section is. In quantum field theory, the cross section, the quantum mechanical object, is defined in a very similar way. And to understand where that definition comes from, it's useful to review what's going on in the classical theory. So the type of experiment we have in mind is we've got a beam of point particles. These are point particles that are moving with some velocity v towards some targets. Which are at rest. And we'll assume that these target particles are spherical with radius r and are uniformly distributed. In some volume. And likewise, we'll assume these point particles are uniformly distributed in some volume, and we'll assume that the let's call these particles the B particles, and these particles the A particles. Let's assume that the length of this bunch of particles is v times some time, the time it takes the bunch to pass some point. And okay, so this is the type of experiment we have in mind. And the question we're going to ask is, what is the probability that a given particle of type B, given point particle, will interact with a given spherical target particle, or particle of type A? And, well, that's basically just a geometry problem. So if we look down the beam, so if we look from this direction, let's assume that this outer circle has cross-sectional area A. So if we're looking down the beam, the target particles will be distributed. The relevant target particles, the particles that have a chance of being hit by one of the point particles, will be uniformly distributed in the area that's common to both beams. We can imagine if there's some extra particles up here that where no point particles go by, they're not relevant. So these particles will be distributed in the area common to both beams, which is A. And then the probability that a given particle of type B will hit a given particle of type A is just the cross section of the particle of type A divided by the area common to both beams. So we're making the assumption here that there's no multiple collisions, so the probability is low. We can neglect that, and these particles are dilute enough that they're not overlapping. But with those assumptions, this will be the probability that a given point particle hits a given target particle. And, well, we can relate A to some of the other quantities we have here. So this cross-sectional area, if we assume that these point particles occupy a volume, which I'll just call vol, then we can also write the area as Bt divided by volume. So classically, there's a relationship between the probability that a given two particles collide and the cross-section of the target particles. And basically, if we want to carry over to the quantum case, we just assume that this relation holds. So quantum mechanically, probability is something we know how to calculate. And we can relate the cross-section is defined, or the differential cross-section. Let's look at this for an infinitesimal version of this equation is defined to be the infinitesimal probability times the volume divided by Bt. And so this is a measure of the interaction strength. So you might ask why we don't just compute the probability that some particular particles will collide. Well, in quantum field theory, the interaction volume and time are generally infinite. So in order to get something we can measure, we need to look at this quantity instead of the differential probability directly for most purposes. Okay. Any questions on this classical case?
I was confused a bit because this capital A that you defined here, sigma by A,
yes,
is the cross-sectional area of the targets, right? I mean the total.
This A, so this A is the common area to both beams. So it's the area, the cross-sectional area in which there's a chance that a B particle could hit an A particle. So we're imagining these, we've got some cloud, say the cloud is like this, it's moving towards some target particles. They might not align perfectly, and only the area that overlaps is relevant.
Okay, right.
And so for this volume, I guess it should be the volume that passes through the target particles. Okay.
Why should that volume be the volume that passes through the target? So if you're, I mean, given like a bunch of particles, there'll be some that will just miss the targets, like are too far away from the targets to hit them at all. But then they've like a zero.
Well, in particular, you can imagine some of the volume that these particles occupy is not going to pass by any of the targets. So we want to throw that part away. So for the simplest case, we could just imagine that all of the targets will pass by, all of the point particles will pass by some target, and then we don't have to worry about that. We could set up our experiment like that. Okay. So this is what we're going to compute. And for the most part, we're interested in 2 to n scattering, almost exclusively. Basically just because it's very hard to collide more than 2 particles at once. And so we can write the differential cross-section as differential probability. So probability, sorry, I'll just write an expression for the differential probability. We'll put that back into the cross-section form then in a second. Differential probability, so that we go from some initial state to some final state. Well, it should be proportional to the transition amplitude from I to F squared. But, well, so it would just be this expression times the differential momentum for the final particles. We need to, for the final particles, we collide 2 particles. We can set up our experiment so we know the initial momenta. The final particles will have some probability of scattering off at different angles. And so if we want to compute a transition element to some final state with specified momenta, we need to specify the range of momenta we're looking at. Because if we just specify one particular set of final state momentum, the probability is going to be 0. We need to integrate that over some finite range of final state momenta to get a finite answer. So this is kind of what you'd expect. We also need to be careful of the normalization. The probability should look like. So first of all, are our initial states and final states unit normalized? So we're looking at momentum eigenstates, and yesterday we looked at, we noted that we chose a Lorenz invariant normalization. So the amplitudes like this, 1 particle, P and K, K and K. This is not unit normalized. If we had a P and a K, it would be a delta function. We chose a Lorenz invariant normalization for our 1 particle states, and similarly, our multi-particle states are not going to be unit normalized. So we need to account for the normalization of our initial and final states. And so here we're looking at the we're eventually going to integrate over the final state momentum. So there's not just a single possible outcome for the momentum in our scattering experiments. But we need to make sure that this measure is normalized appropriately. And so the easiest way to see what the correct normalization is to imagine we're in periodic space. With volume equals L cubed, just a cube in every direction. The period is L. Then the momentum will be quantized. So Pi will have components that are 2 pi over L times some vector of integers. And in that case, summing, we want to sum over the ends. That would be the normalized way to sum over the final momenta in the periodic space. And that sum over n then becomes, in the infinite volume limit, an integral over final momentum. We get a factor of 2 pi cubed times L cubed, which is the volume. So our measure should include a factor of 2 pi cubed, as we probably expected, but also a factor of the volume. Another way to see this is, this is a dimensionless combination. So this is dimensionless. We're looking at ratio of amplitudes. And this is also dimensionless, which gives us the dimensionless probabilities we'd expect. So this is our formula for the differential probability. And we're interested in initial states where we just have 2 particles, the momentum eigenstates, and final states that are also momentum eigenstates have n particles. Any questions on that formula? Okay. So what we're interested in relating cross-section 2 are these S matrix elements. We can say it's convenient to think about what we expect our S matrix elements to look like, or what the S matrix itself should look like. So in a free theory, we expect that there are no interesting transitions, no interesting scattering, and basically the evolution is just trivial. So nothing interesting should happen in a free theory. So the S matrix should just basically be the identity matrix. So it's useful to separate out the interesting physics from the trivial physics. There's no interactions in a free theory. And this T here is what's known as the transfer matrix. And it's defined like this. So this looks like it's some expansion of an exponential, but actually not quite. This is just definition that the S matrix is related to the transfer matrix by just adding or subtracting off the identity. And so this transfer matrix contains all of the interesting physics. And so what do we know about the transfer matrix? Well, one thing we expect is that there should be no transitions unless energy and momentum are conserved. We are dealing with quantum theory, so we don't know much. Interacting quantum theory, we're not making any assumptions yet about what the interactions should look like, but they should conserve energy and momentum. And so this matrix should reflect that energy and momentum conservation. And so we expect, and when we do computations, we'll actually see that this expectation is borne out. We expect that this transfer matrix should be 0 unless energy and momentum are conserved. And so it should be proportional to a delta that conserves energy and momentum. And what's left over is called M. And so the matrix elements, so M is often, so F I M. I is also known as the matrix element. That's, we just implicitly understood what matrix we're referring to. So this is also referred to as the matrix element, and this is often abbreviated in a slight abuse notation as just IM. So you'll often see this if the process is understood. It's an extremely common usage that is in fact a slight abuse notation. Okay, so the interesting part of this matrix element, FSI, let's assume that I and F are different, so this one part won't contribute. Well, what we're interested in computing the differential probability is the square of this. And so if I is different from F, then what we have here is 2 pi to the 8 times a delta conservation of momentum squared times F I M I squared. Now this should worry you at least a little bit. One of the things I emphasize in the front end is that the theory of distributions is a linear theory. It doesn't make a lot of sense to square delta. But as we did when we ran into a problematic expression involving a delta yesterday, we were looking at the ground state energy. We saw that there was a delta of 0 there. We can think about one of these deltas as forcing the argument of the other one to be 0 and interpret that delta of 0 as, like we did before, well, last time it was just the volume of space. This time it's a 4-dimensional delta, so it'll be the volume of space-time. We can just write this as the volume times t. So we'll interpret one of those deltas. Okay. So we're making some progress in understanding our formula for the differential probability. Let's next look at the denominator, the FF and II terms. Those are also going to, as you may expect, involve factors of the volume. So involve deltas of zeros. We normalized our one-particle states to be proportional to delta functions. So our one-particle normalization was dk 2 pi cubed 2ek delta p minus k. And so when p equals k, we've got here a delta of 0, which again we can interpret as a volume. This is a 3-dimensional delta. So k 2 pi cubed 2ek times the volume. And similarly for the initial and final states. So the initial and final states, the initial state, we have 2 particles. So we just get the 2 pi cubed times the delta should be the volume. So there shouldn't be a 2 pi cubed. Sorry about that. Yeah, there should also be a 2 pi to the 4th here.
Sorry. Are we forbidding M from containing any additional deltas?
Not at this point, no. So what we'll...
Because if M is a function of additional deltas, we have the same problem arbitrary number of times.
That's right. What we'll find... That's something we'll examine more when we look at the interacting theory, but we'll find that for the interesting scattering processes, there's no additional deltas. Find what interesting means later. But we'll come back to that. So there are two factors of the volume in normalization of the initial state and n in the normalization of the final state. Okay. So let's combine what we have so far. So far we have dp. Let's collect some of our factors. So we've got a im squared. We have a factor of t in the numerator. That's the only time we have a 4-dimensional delta. So that's the only factor of t we're going to get. this, we also have from the denominator factor of 2 ek1, 2 ek2, and I'll leave and if we count factors of volume in the measure, in the dp cube term, we have n factors of the volume, which cancel off the n factors of the volume from the normalization of the final state. So those cancel. One factor of the volume in the denominator from the normalization of the initial state cancels from one factor of the volume in the numerator coming from this delta. So we're left with just a single factor. N plus 1 cancel. And everything that I didn't write so far, I'll collect in d phi. And d phi, what I didn't write are the remaining delta. We have a energy momentum conserving delta. And we also have our measure over final momenta. We've got this dp over 2 pi cubed, and also the energy, 2 times the energy of final state particles. And that's it. So this is what's known as the phase space measure. And
what happened to a 2 pi factor? Well, the 2 pi to the 3 delta.
should be 2 pi to the 4. Thank you. And so we've now computed the differential probability. What we were interested in is the differential cross-section. And the differential cross-section is also going to be proportional to d phi. But we have an extra factor of the volume, which cancels our factor of the volume. We have an extra factor of t, cancels the factor of t. And we just get a factor of Im squared is left. We still have the energies. And we now have the velocity. So this formula together with this formula are our final expressions for the differential cross-section. And, well, that involves the phase space, which is here. So we have a relationship between the matrix elements and the differential cross-sections. Katie.
We're using non-relativistic velocity in the definition of the cross-section, right?
Okay, so here, most of the textbooks define the velocity here just to be the magnitude of the difference in the velocity of the two initial particles. You sometimes see other definitions that agree with this one, as long as we're in the frame, in a frame in which the initial and final particles are collinear, which in practice is the only case we ever care about. But sometimes you see other definitions that make this thing Lorentz invariant. This yeah, so this is, we are in a special relativistic case, so we should use the relativistic law for adding velocity. Okay. So we now understand how to compute or how to relate a cross-section to the matrix element. So this matrix element contains all of the interesting physics that depends on which theory we're looking at. So for most of the rest of the course, we're going to be focusing on how to compute these matrix elements. And in this formula here, we've separated out the interesting physics, the interesting dynamic part of the calculation from the phase space, which is just the kinematics. So this part of the expression doesn't depend at all on what theory we're talking about. It only depends on the number of particles. And so if we want to calculate a decay rate, it's going to be very analogous to what we just did. So we can basically reuse almost all of our calculations from before. So if we have an unstable particle, most often there are multiple ways it can decay. So if we have, say, a tau particle, it could decay to muon and neutrinos or electron and neutrinos. And so in practice, if we're going to calculate the lifetime of the tau or the decay rate of the tau, what we'll do is so the decay rate is 1 over the lifetime. We'll look at some particular way that that particle can decay. That particular channel can then give us a partial decay rate. So for instance, we can calculate how quickly the tau decays to muon and neutrinos. That's an easier calculation. Then we can have a specified initial state and final state. So that's a calculation we can do. If we eventually want to get back to the total decay rate, we need to sum over all possible decay channels. Or and so the differential partial decay rate is what we'll be directly calculating. And so almost nothing changes compared to what we did for cross sections. For a partial decay rate, that should have units of 1 over time. So it's going to be equal to the differential probability divided by the time in which the interaction can occur, which is almost the same formula we had before. The difference will be 2 differences. One, instead of factor of volume over V and T, we just have a 1 over T. And the other difference is in the initial state is just a single particle. So we also lose a factor of volume in the denominator, and we also lose a factor of energy. So that means we can basically just carry over our results from before. Phase space over the final particles is the same. Still have the matrix element squared. And we just have a single factor of 2ek. That's the energy of the initial particle, or just the mass in the rest frame. And so there's our expression. Almost no work given what we've done for the cross section. So you may worry about putting an unstable particle in the initial state, which we're taking to be in the infinite past. But really, what matters is that the interactions occur over a finite time, and we'll see that in our calculations that it won't pose a serious problem that we have an unstable particle in the initial state. So an issue we can keep in mind that we'll come back to later. Okay. So we have our formulas for the K rate and cross section, and because the phase space is independent of the theory, it only depends on the number of particles we have in the final state, and the masses. We can simplify the phase space for the commonly occurring cases. So the most common cases are we have either 2 or 3 particles in the final state. Those are the simplest interesting cases. And basically, because our phase space involves, so if we look at our phase space over here, it involves a delta, energy and momentum conserving delta. We can use that delta to simplify our phase space. And so it'll be useful to do some of that work now. And so the case we'll consider now is the simplest possible case. Let's assume we have 2 particles in our final state, and both are massless. So in that case, our phase space just 2 pi to the 4th. That's the momentum conserving delta. And the integral Lorentz invariant integrals over the final momenta. Okay, so if we look at the phase space, one thing we notice is that it's the product of a Lorentz invariant delta with 2 copies of the Lorentz invariant measure. So this is Lorentz invariant, and we can evaluate it in any frame, and our results will be good and equally valid in any other frame. But for practical purposes, it'd be useful to choose a frame, and the center of mass frame is the obvious choice. So in the center of mass frame, sum of the initial 3 momenta is 0, and the sum of the initial energies is takes some value, which I can call ECM. Okay, so ultimately we're going to be wanting to integrate over the phase space. And so the integral over the phase space Well, we can use the 3 components of this delta to do one of the integrals here. And if we do that, well, we've got 4 factors of 2 pi in the numerator, 6 in the denominator. We're left with 1 factor of 2 pi squared. Still have the energies. And we're left with 1 delta. Energy conserving delta. And 1 momentum integral. So suppose we use the delta to do the integral over 2 momenta over P2. And the first delta basically has the effect of setting P1 equal to minus P2. You know, in the center mass frame, the total 3 momenta has to be 0. So this is all evaluated at P1 equals minus P2. Okay. So that's progress. If so far we haven't used the fact that our final particles are assumed to be massless. If they're massless, then the energy is just equal to the magnitude of the 3 momenta. And since the 2 particles have equal and opposite 3 momenta, that tells us that the energies of both of the particles are the same. So then we can simplify this a bit more. So over here, got 1 over 16 pi squared, collecting our numerical factors. E is the magnitude of P1. We can go to spherical coordinates. It's useful because we have information about the magnitude, but not about the angle. So have P1 squared d omega dP1, and we still have our delta now of 2 P1 minus ECM. Okay. And so, well, we can, in this form, we can now do the integral over the radial direction over the magnitude of P1. And, well, the only thing to keep in mind here is that we have this factor of 2 in front of P1. So this, again, is delta of a function. And we need to use our formula that delta of a function is delta at the zeros over the derivative of that function at the zeros. So this will give us an extra, doing this integral will not just set P1 to be half of ECM, it'll also give us a factor of a half. So what we're left with then is these factors of P1 squared cancel. And what we're left with is the integral d omega over 32 pi squared. The half comes from the delta. Okay. So that's what we can get from integrating the phase space using the deltas. And because the only thing we used to do these integrations were these deltas, this derivation works if we insert an arbitrary function of P1 and P2 into the integration. In particular, if we write d phi 1, d phi of f of P1, P2, because we only use deltas, that's the same as the integral d omega over 32 pi squared of f of P1 and P2 evaluated at P2 equals minus P1 and P1 equals a half ECM. That's true in general. And another way we could write this, assuming f is also Lorentz invariant, it's just this is evaluated at sum of p is sum of k. K is our initial momentum. And so you often see this abbreviated as d phi 2 is d omega over 32 pi squared. And that's what this equation means. This equation really means this above one. Any questions on that? Okay. Happy birthday. I'll leave that up.
It's up
Oh, no.
so it's fine.
Yes.
Take a picture, I guess. Hopefully she shows up for step. Just cover it back up. There's a person wearing some platforms. Yeah, that's an option. Super weird. Why?
Okay, so the last part of class, I thought we'd go through an example of how to compute a cross-section. So obviously we haven't learned how to compute matrix elements yet, so I'm just going to give you an example. It'll be an example that we'll return to later. You'll see where this matrix elements come from later in the course. But computing a cross-section is there's lots of steps to it, so I think it's useful to go through how you can approach these calculations. And so we'll do part of it today, and we'll come back over the next week to do the other steps in the calculation later next week. We'll look at that. So this example is in a toy theory, one that we'll study again when we learn about how to compute matrix elements. And it's a theory with two scalar fields. So these are two scalar fields. One is a real scalar field. This is a real scalar field. And call it a meson. This is kind of a toy model that describes the interaction of nucleons with mesons. So here I've just written the kinetic term so far. So these two fields, we'll assume they interact. An interaction term that's minus g times rho star rho phi. And also that they have mass. The nucleon mass big M and the meson mass small m. And so this is a toy model for the interaction of nucleons with mesons. So here everything's a scalar. As in my part of the course, we're just going to deal with scalar field theories. Those are the simplest. Gong will teach you how to deal with spin. So the difference between this and a more realistic model is that nucleons are fermions with spin a half. So this model accounts for some of the features of the interactions of nucleons with scalar particles called mesons, but we're not accounting for the spin of the nucleon. The interaction term does look like this. Even if we look at a more realistic model that incorporates spin. So this includes some of the features of the interactions of these two particles, but it's mostly we're looking at it because it's a simple toy model that we can get a feel for how to do these calculations. Okay. And so in the notes, I've kept the masses. Those of you following along in the notes, notice what's in the notes is a bit messier than what I'm going to do here, just for simplicity to illustrate the general procedure. So this is in the notes. Here, I will set m equals 0, just so we can get an idea for how these calculations work without cluttering them too much with masses. Okay, so one process that can occur in this toy theory or in the real theory of interaction of nucleons with mesons is we could scatter two nucleons and get two nucleons. The matrix element, which we'll learn how to compute next week for this process, if the initial nucleons have momenta k1 and k2, and the final nucleons have momenta p1 and p2, is just minus ig times I over k minus p1 squared plus I epsilon plus I over k1 minus p2 squared plus I epsilon. This I epsilon is something we'll take to 0. At the end of our calculation, you may recall it made a brief appearance in the front end. We'll see what this means, where this comes from, again next week. This is the result. Just presenting it here we'll learn where this comes from later. Okay, so if we want to compute the cross section, what we found is that the cross section is just given by matrix element squared times the phase space over 2 pk1 to pk2 times b. But there's one thing we haven't accounted for. So if we're interested in getting the total cross section, what we want to do is we want to integrate over all possible inequivalent final momenta. The process we're interested in has two identical particles in the final state. So if we integrate over all possible values of P1 and P2, we'll be double counting because the state with P1 and P2 exchanged is exactly the same state. They're identical particles. So if we don't want to overcount, we have to divide by 2. So this is sometimes called a symmetry factor. So this is a symmetry, has to do with the symmetry of particles in the final state. So keep in mind that this is a distinct factor from the symmetries factors we'll be talking about next week when we learn about how to calculate these matrix elements. So the symmetries of phase space and symmetries that are involved in calculating the matrix elements are different things. I haven't told you what the symmetry factors involved in calculating matrix elements are yet, but I just want to warn you already that they arise for different reasons. Okay, so this is what we want to calculate. And we can work in the center mass frame. It always makes things easier. So in the center mass frame, our momenta have relations. K1 and K2 have to have the same energy because they have to have equal and opposite free momenta, just like before. And similarly, P1 and P2 have to also have the same energy as each other and as the initial particles, because their energy is half of the total energy. And they have, again, equal and opposite 3 momenta. And so let's assume that there's some angle theta between E and K. So the only thing that can change, so the energy is fixed. The only thing that changes, it can scatter off at some angle. Okay. And so that tells us that sigma, using our result from before, computed the two-body phase space for massless particles. 1 over 30 d omega over 32 pi squared im squared over 8e squared, because v is 2. In the center mass frame, particles 1 and 2 are approaching each other at speed of light because they're massless. And so what's left is to evaluate im squared. And im squared is g to the 4th, 1 over k1 minus p1 squared plus 1 over k1 minus p2 squared. Now, because we have massless particles, k1, k2, ki squared, and pi squared are all 0. These are massless particles. So the only terms that survive here are the cross terms when we square out these denominators. And the cross terms are k1 dot p1, which is using our explicit expressions for k1 and p1 there, e squared minus k dot p, which is e squared 1 minus the cosine of theta, because these have an angle of theta between them. k1 dot p2, same thing, with the opposite sign. And what we get here then is g to the 4th, 1 minus 1 minus cosine theta, 1 over 1 plus cosine theta. And so you combine that and get differential cross-section, d sigma. I'll write it one more step. This is 2 over 1 minus cosine squared theta squared. And so d sigma, d omega, is then combining our results. D to the 4. We've got here factor of 32 times 2 times 8. So we have, and also a factor of 4 here. It will cancel off 2 of that. So we get, oh, I missed the factor of 4 here. This should be, we get a 2 from the cross term. So there should be a factor of, extra factor of 4. Cancels this. So we get if.
Where did in the d sigma on top of the board, where did the 8 come from? Why is it not 4?
The 8 comes from the fact that v1 minus v2 is 2. So in the center mass frame, we have one particle, say, coming from the right at the speed 1, and one particle coming from the left with speed minus 1.
Should there be a factor of e to the power 4? This factor of e.
E, yes. E should be here. E to the 4. Thank you. 4 e to the 4. It comes from here. So putting things together, assuming I didn't make other algebra mistakes, we get this as our final expression for the differential cross-section. So we notice one thing immediately from this. So this diverges near theta equals 0. And even worse than that, it's not integrable. So this is as far as we can proceed in the massless case. So in the notes, I included the masses and showed that this problem goes away. You get some expression that's quite a bit messier, but is finite. There are extra divergences in theories with massless particles that can be understood. It's not something we're going to discuss in this course or 52, possible topic for 53. But basically, so massless particles can cause divergences. So one way to think about it is that if you have a very low energy massless particle, those are very difficult to detect. So real detectors only detect massless particles above some certain energy threshold. And if you account for the experimental detection capabilities properly, you can avoid IR divergences like this. That's one way to think about it. There's several other equivalent perspectives, but that's the reason why we get a divergent quantity here. Theories with massless particles have some additional subtleties that we won't address in this course. But it's interesting to see that you run into some problems like this, even in a very simple calculation. So we've done today, related cross sections and decay rates, things we can measure in the lab, to matrix elements. And that's basically going to be the focus for the rest of my part of the course, is how to compute these things. And so it's going to take us several lectures next week. And so that's where we're going. Any questions? Okay. I'll see you in tutorial this afternoon.